Today we have a special seminar. We have Kiyoshi Suyehiro, who we've had the pleasure of hosting for the last couple of months as our Tuve Fellow. It's a particular honor to work with Suyehiro-san for a few reasons. One is that he's actually got a very long association with DTN, going back as a postdoctoral fellow here in the 70s, but it even goes back before that because he's a legacy member of our department. His father was here as a postdoc in the SUE. So we've got a long association with him. We're very happy to be able to keep it up. He's got such an impressive list of credentials. I'm sorry, but I'm going to have to default and read them to you. He was a former executive director of the JAMSTEC agency in Japan Agency for Marine Earth Science and Technology. I think many of us in the fields of geology know that agency and the amazing quality of work that they've done. He's still a principal scientist with JAMSTEC. He was the president and CEO of the IODP, Management International Ocean Drilling Program. He was director of Deep Sea Research Department at JAMSTEC, as adjunct professor at the Tohoku University, and professor of ocean research at the University of Tokyo. So today we have the honor of the Tuve Lecture. We're inside Earth Through the Seafloor. Thank you very much.
Thank you very much for the introduction, Rick. So today I'm very honored to give this seminar, and I'm happy to be back to DTN on this occasion, as well as so many times before. And I hope to make my more trips to DTN more frequent in the future. So today my talk is title is here, and the picture you're seeing is, of course, far, far away, and this was taken from a Japanese lunar orbiter looking at the Earth, and so it's just a nice photo, and I didn't, it has really nothing to do with me. So this is the map of the Earth's surface, and I've seen this in the research building, so you must be very familiar with this. And as you know, 71% of the Earth's surface is covered by oceans, and to understand, everybody would agree that to really understand what's going on inside the Earth, you would like to also know what's beneath the oceans and what kind of difference persists down from the oceans or from the continents. And plate tectonics tells us that ocean lithosphere is the plate thermal boundary layer, one might say, is the agent that mixes the mantle and important for the dynamics of the Earth. So, so my motivation and many of my colleagues in marine seismology face this technologically challenging part of the Earth, but we know that the scenes of actions are out at sea, so we've been struggling with trying to put instruments on the sea floor for so many decades, and I think we are finally succeeding to get data back in the way that can be used to get some significant results. So that's what I'm going to talk about. And here is the bottom sentence is what I really want to convey in my talk. The observational capability, that's the seismological observational window at sea, must widen in frequency range, dynamic range, and lengthen in time without spatial, that is water depth or geography limits. And that's almost identical motivation for seismologists working on land. We're just extending that to the oceans. And by the way, I've taken this figure out of USGS earthquake hazard map, and you see that plate boundaries are where oceans meet continents and where earthquakes occur, as you are very aware of. So the questions I'm going to address today are given here. First of all, I would like to touch on how are oceans different from continents. like just I said. And after so many years, we are not quite sure whether lithosphere is a thermal boundary layer or either whether we can see the bottom of the ocean lithosphere by seismological method. I will show you that there seems to be some evidence that indicate that the lithosphere bottom can be seismologically detected. And the other feature I would like to touch on is the oceanic island arcs, because we found that in the Izu Bonin Island Arc, which is an oceanic island arc, for some reason had crustal structure which resembles that of the upper crust of the continent. What does that mean? And of course, as a seismologist, we are always interested in learning about earthquakes and tsunamis, and particularly since 90% of seismic energy is spent at plate subduction zones, and also because Japan is subject to these hazards, I would like to introduce you to some of our works done in the for the Sumatra 2004 earthquake and tsunami, as well as 2011 Tohoku Oki earthquake and tsunami. So here is a figure study done by Chao at Tohoku University, and this was written in 2004, but the situation hasn't really changed over the years, so I'm showing this. This is what the seismologists call checkerboard test image, and what this tells you is that if the Earth, you gave perturbations to the standard Earth model at, right here it says 50 kilometers, 290, 559. So we're talking about upper mantle here. And if you perturb the velocity structure by only 1% plus or minus, and these are in 10 degrees grid, so pretty wide, 1,000 kilometers square, and you let earthquakes, natural earthquakes occur and observe them at the existing stations through this standard model with these velocity variations. And then can you invert your observations back to what you put in? And so ideally you should get black and white circles all over, but you don't. In particular, you don't see that at less than like 600 kilometers depth. And this means that the current geometry of earthquakes and stations is such that you cannot resolve the structure of oceans in the upper mantle very well. And that also says that the oceanic lithosphere structure is still not quite well known. From normal global seismic network observation studies. So what can we do about it? And as I said, Japan is situated in the Western Pacific, where a lot of earthquakes occur. And I just looked at earthquake events over magnitude 7.5 between 74 through like just now. And you see these earthquakes, and if you look at all the earthquakes around the world, there were 160, and 109 occurred in this part of the world. And as you know, there was none in the mainland USA. Good for you. So our interested area has been here. So I've worked on studying oceanic lithosphere in the northwestern Pacific Ocean, and I've done works in the Back-Arc Basin, which I'm not going to touch on today, but I will touch on Sumatra earthquake and Tohoku earthquake here, as well as the structure of the oceanic island arc right here. The Japanese islands were split from Eastern Asia, so this is continental in origin. So what we are interested in is what makes a normal ocean turn into something different. And then this is the vertical section cartoon drawn by Tatsumi, and this is the volcanic arc, which is equivalent to what I've been saying as oceanic island arc, and the plates of dust like here, and so many actions are taking place here, but in most cases these are covered by ocean, and in most cases this kind of figure remains as a cartoon and not too quantitatively defined. And so I'll be talking about this part, the crustal structure, and then also I will touch on how the big earthquakes occur at subduction zone. So before diving into the scientific topics, I just want to briefly cover the developments we made in terms of instrumentation. Nowadays, operation of what we call free fall, drop from the research vessel and pop up. You send acoustic signal to release weight for ocean bottom seismographs to come up, and they do nearly 90% to 100% of the time. And while the OBS is down on the sea floor, you can do active experiments like shooting air guns or sometimes explosives, and as well as recording earthquakes. And this kind of operation can be weeks, months, and even longer than a year. The clock accuracy has really improved to make that reliable. In the 90s, or it was in the 90s that GPS came along, and so before 90s, you deploy your OBS and you try to go back to the place where you put your OBS, but you could easily be off by miles. So that's no longer the case. And the kind of OBSs we have, I mean, I'm just showing you Japanese examples, and there are many other kinds in Europe and the US. But basically, the essential part is the same. We utilize different seismometers and seismic sensors like natural frequency at 4.5 hertz or 1 hertz, or even broadband that goes beyond hundreds of seconds to the long period. And we can also install accelerometers to try to record strong motions. And we are recently, as I will show you later, we are discovering that ocean bottom pressure gauge at very high resolution is giving us very interesting data. So we are able to record them almost as much as possible because of the advance of digital technology. And so we've come a long way from the very early years, but I think we can really plan on doing OBS experiments in almost anywhere in the ocean worldwide. And this is one of the recent developments, and this one uses a ceramic sphere to withstand really deep ocean depths, and this has 11 kilometers rating. And those glass spheres usually can be installed at 6,000 meters water depth to 7,000 meters. They implode if you put them in deeper waters. And of course, our eventual goal is to expand the seismic global network into the oceans, and this has been going very slowly, unfortunately, because of the cost and everything. But we did try to establish such kind of network in the western Western Pacific part of the world in the 90s, late 90s, and these orange dots are where we succeeded in placing borehole broadband seismographs, and these yellow dots are where islands are. So these are basically land stations. So, but with these key observatories in the boreholes, joint with Ocean Drilling Program, we could sort of establish about a 2,000 kilometers span seismic network for some time. And so I will give some results from these stations. And this is just a photo showing how things are done on the sea floor. And of course, it's very deep, and the access, first of all, drilling is done by a drill ship, and then installation is also done by drill ship, but then servicing these stations are done by remotely operated vehicles. And so it's costly and time consuming and very high risk, but if you succeed, you get very unique data that otherwise you cannot get. So what kind of noise spectrum do you have? And this is a bit technical, but these are the figures from, as given here, Araki, Shinohara, Sachs, Linde, and others. My name is at last of this list, so, but so you know that we've worked together with Selwyn and Alan on this, although they may have forgotten about this paper. So looking at the seismic observational window that I briefly mentioned, this is frequency in hertz, 10 hertz, 1 hertz, 10 seconds, 100 seconds. So this is the kind of frequency range we're talking about when we try to register earthquake records. And the dynamic range has to be very wide, but of course we are limited by the instrumentation, which currently is about 24 bits. So, and these dotted lines are what seismologists call high noise model and low noise model, and so what this tells you is that if your station is situated in a very, very quiet place, like in the middle of desert, in the middle of continent, then the noise level would look like this. It's not flat, there is structure. And if it's noisy, this is lifted like so. So what did we find on the seafloor and on the in the boreholes? These are borehole data, and I guess I should not go into too much detail, but we can explain the shape, and we are getting noise levels not as quiet as on the quietest continental sites, but moderately quiet in the boreholes, whereas, sorry that this is much smaller figure, but OBSs on the sea floor are very much subject to noise at longer periods as well as at high frequencies. So this cartoon tells you why boreholes are superior to sea floor. It's that the OBSs are normally planned on soft sediments and subject to, this is really exaggerated sediment deformation, but this responds to the change in the sea surface, pressure and wind. So seismometers in more competent rock performs better. But of course, as I've been telling you, it's very much more expensive. So the one other way is to place a great number of OBSs to reduce the noise. And the current trend is going in that direction. So to summarize what I've just said about technologies, Tens to more than 100 OBSs can be deployed to record several to more than a year seismic records continuously at various dynamic range and frequency ranges to near 10-kilometer water depths. The deepest water is more than 11 kilometers deep, so it's not really 100%, but near 100% coverage can be attained. And of course, Arctic Sea is a challenge. Subsea floor boreholes provide stable and quiet environment compared to seafloor for long periods, as I just showed you in the previous slide. So now we move on to the results we got. First, I will start with the ocean lithosphere, and as you can see, this is the Western Pacific. Here's Shatsky Rise. This is an anomalous feature. Bathymetric highening in itself is interesting, but I will not go into that. We will be talking about the normal oceanic lithosphere here, and for this borehole observatory, we did airgun survey to look at the details of the oceanic crust, and we found that the oceanic crust was as expected, because there have been so many surveys over oceanic crusts in Pacific Ocean, Atlantic Ocean, and others, that we didn't find anything anomalous. But if you go below the borehole, what we call PN and SN velocities, which are the seismic velocities right beneath the borehole, had anisotropic signature, and P and S wave, well, this is about P wave, was faster in this direction, which is more or less normal to the magnetic lineation. And these white lines are the magnetic lineations, and these numbers are million years old. The plate motion is in, as this green arrow shows, about 7 centimeters per year in this direction. So we interpret that this is indicating that the anisotropy is sort of embedded when the oceanic lithosphere was originally generated, and not looking at the mantle flow at the top of the uppermost mantle. This 13% is from previous study in the 70s and by Asada and others, and this also showed anisotropy and also perpendicular to the magnetic lineation. So I think in this study they did not use air guns. So in terms of the figure, I think this number 5% is more reliable, but the general feature is the same. And so what can you do with just a single station? Well, there are earthquakes occurring at the rim of the Pacific Ocean, and you can record these. And in the fast direction, these are stars, epicenters, and in the slow direction, these are the squares. And unfortunately, because of the way geometry is, we could record in separate distance ranges for slow direction here and for fast directions here. And Shinohara and others have concluded from these data that although airgun data showed 5% anisotropy at the top of the mantle, it actually increases, and this indicates that the slow direction is really slow, and to explain that at least down to 80% the anisotropy increases with depth. And unfortunately, beyond 80 kilometers depth, you lose sources of data, and you cannot say anything about fast direction. But this shows that it's much slower than the normal mantle's average structure. So we concluded that the low velocity zone may persist down to 200 kilometers. But we don't have data enough to say anything about these depths, except that we do observe converted phases meaning P wave turning to S and S wave turning to P at these famous phase change boundaries, 400 kilometers, 670 kilometers. So we could identify these, and but this was as far as we could go. So and this is as far as we could go even today. So I hope that this can be improved in the near future with new instruments. That is to have more instruments distributed, since we cannot change how the earthquakes occur. There was another study done by Kawakatsu and others who looked at only at receiver function. Again, it's looking at PMS converted phases, and they sort of tried to reduce the noise by stacking the data. And now we are looking at our station WP1 in the middle of the Philippine Sea, which is somewhat younger than the Western Pacific Ocean, much younger. And this is the record. And the point is that Kawakatsu and the others interpreted these to indicate a discontinuity that causes these converted phases. And because it's showing blue, the velocity is going negative from as we go deeper. And they thought this might be the bottom of the lithosphere, so LAB, lithosphere, stenosphere boundary. And blowing up this part, actually we see that not just Western Pacific, West Philippine Basin, but also Paris Villa Basin is being sensed. And so we see slight difference in the appearance of LAB depth for Paris Villa Basin as compared to Western Pacific Basin, and this is older. So it sort of fits the idea that lithosphere cooling occurs with age. Now, the same thing could be done for the Northwest Pacific plate, and the interpretation is that lithosphere boundary is right here, and this may not be too convincing here, but if you look at land seismic stations data, there are so many that you can easily define there's some kind of boundary going down, and this may be the extension, or this may be the extension of the boundary here. So this is the point I was making about many more stations. OBS on the seafloor may be as good as few borehole stations. And if you have very many, you can map this out. So for the ocean lithosphere, broadband seismographs in ocean drilling program boreholes and OBS recorded nearby active sources and distant earthquakes to provide accurate view of the oceanic crust and upper mantle, as you've seen. And there's the anisotropy, and this is the actual equation that fits nicely with the data. And ocean crust is consistent with previous results, and the actual thickness is a bit less than 7 kilometers below the sediment to the mohole. And upper mantle phase changes were detected at these depths from separate receiver function analysis. And as you've seen, we may have detected lithosphere, stenosphere boundaries, and which differ with different ages. However, I think you will have got the impression that if you compare these results with what people infer from land observations, we are still very far from well understood. And that's all owing to too few stations you need more stations distributed geographically and to be able to register many earthquakes. So that's one direction for the future. Now, moving to oceanic island arc. We did in the 90s OBS experiment right here across the northern part of the Izubonin Island arc. Although we crossed the trench, we could not have instruments to go at deeper depths. So basically what we obtained by this profiling was this crustal structure beneath this island arc, oceanic island arc. And geologists tell us that these features were born out of normal ocean, and these were created because about 40 million years ago, Pacific plate started subducting against Philippine Sea plate, and the subduction caused magmatism to occur, and these were created. But before we did this experiment, nobody really knew how the crustal structure was under these bathymetric heights. And so this is the figure we made in '96, and as you can see, the key thing we thought from this figure, very unexpected, we were actually interested in how thick was the crust, but what surprised us was this 6 kilometers per second to about 6.5 kilometers middle crust part, which comprises about 1/4 the crustal volume here, which something lacks in normal oceanic crust. And seismology can only go this far, but if you look at other evidences such as dredge samples, and because this arc is colliding against Japan here, there are some evidences that abducted tonalites are found. So we thought, and this is indicative of upper crust continental P-wave velocity. So our conclusion was that we are finding continental crust to be generated out of normal ocean. And what would be the fate of this oceanic crust volume? We think this may be contributing to the growth of continents. And so is this ubiquitous? We did another experiment down in south here, and we also see a similar feature beneath the Mariana Arc, as well as beneath the West Mariana Ridge. This is to say that the Mariana Trough was opened to separate the ridge to these two ridges. So this, what we call middle crust, must have been generated before the Mariana Trough was opened, because this became extinct ridge after separation. So Kodara and others performed another survey along arc with many OBSs and have identified the same feature persists from north to south. So we do have this continental crust signature born out of normal ocean. And petrologists, geochemists are trying to explain how these are generated, and then also how they might be added to continental mass. To summarize this part, multiple OBS with air guns explosives and local earthquakes provided a first total look of the oceanic island arc crust in the northern Izu Arc. Where active rifting is ongoing, the crust is thickest, and the middle crust possesses the signature of continental rock. And this feature is found at West Mariana Ridge, and I didn't mention this, but also another ridge even further west is the Kyushu Palau Ridge, and we see the same feature here too. So this creation and eventual accretion of ocean island arcs suggests one of the candidate volumes for continental growth. Large igneous provinces, which are bathymetric heights like the Shatsky Rise, or most famously the Onton-Java Plateau, seem to subduct into the mantle without a problem. Meaning that we have done a survey on the Onton-Java Plateau colliding into the Solomon's Arc, and seismological structure shows that everything is subducting. So that's the reason for saying that. Now we move on to earthquakes and tsunamis, and 2004 Sumatra Andaman earthquake was a big surprise to seismologists, and Kanamori wrote a paper in 2006 and sort of saying that normally seismologists have thought from the past examples that the faster that your subducting rate is normal to the trench, and if your plate is young, so more buoyant, would cause plate coupling to be stronger, thus causing larger earthquakes. But in the case of Sumatra Andaman, the plate is not that young, and the speed is not that fast, and so the size of the earthquake is surprising. So that's why I said unexpected in earlier slides. But this is to show that as a seismologist, if you're looking only at the span of era where where modern recordings are available, you are really limiting yourself to only a short period of the whole process of earthquake generations. And I think we need to work with geologists and others to take a bigger view of how things are. Now, in the case of Sumatra, little was known. I mean, as you can see here, this is seafloor bathymetry known before we conducted our survey, and even the seismic data were only registered by distant stations, so we didn't really know where the fault was, how it looked like, how was the big tsunami generated. And so in this case, it's not just seismology, but also diving into these green dots areas by submersibles, as well as mapping by swath bathymetry. As you can see, this is the 3D image of this area. And the trench is somewhere here. And we saw that huge disruption is found at the top of this ridge. This is about 45 kilometers long. But of course, our main aim was to look at the seismicity, and sorry that it's a small figure here, but from OBSs, the aftershocks occurred like so, and without going into details, we believe this A site is where that big disruption was found by submersibles, and the part A, position A, is 50 kilometers from the trench axis. So almost nothing for the first 50 kilometers from the trench axis, and this is quite different from what you saw for the Tohoku earthquake, as I will show you later. And so we deduced that from this observation that the Sumatra earthquake, the main rupture went up through a branching fault, what geologists call splay fault, which has a bigger dip angle than if you just drew a line to the trench axis, and that would cause the uplift of the seafloor to be greater than otherwise, which contributes to the generation of bigger tsunami. Now, we cannot be conclusive here because we've only looked at this part of the whole 1,300 kilometers earthquake fault. So now we turn to the Tohoku Oki earthquake. When this happened, I was at IODP MI, so I could do really very little. And these are results mainly done by my colleagues in Tohoku University and Earthquake Research Institute. So if you recall what happened on that day, the earthquake occurred offshore northeast Japan and caused nearly 20,000 people to disappear. And the tsunami was really devastating. Now, again, but seismologists have to understand why that happened and what exactly was the geometry. And in order to understand where the fault is, here's a diagram taken from a textbook, sorry, in Japanese. But this is the fault, like so. And you can see this as mimicking the subduction plate angle. This is the plate boundary. And depending on the angle of subduction, the permanent deformation differs. So it is critically important to get the data on the seafloor because this orange line shows that in this part of the whole area where the deformation takes a phase change is out in the ocean. So without knowing this part in real data, you just only have to guess. Fortunately, Japanese seismologists were expecting a magnitude 7 earthquake, 7 to 8 earthquake in that area, so they had two kinds of new instruments, not seismometers, but one is GPS acoustic measurement stations and the other is just pressure gauges. And I'm really grateful to the late Fred Spies at Scripps Institution of Oceanography, who really invented this system, and he was very cooperative in transferring the technology to Japan, to deeper waters. And so fortunately we had these from before the earthquake. And this is the pressure gauge recordings, and they were scattered right above the subducting plate boundary, and you can see some went up, some went down, and this is first of a kind observation. And this is the distribution of these instruments, and this is the Japan Trench, and the main faulting large displacements were supposed to have taken place here. And if you try to explain the observations just you saw in the previous figure, this is the data, uplift, co-seismic, and I think you should look at this figure alone. And if you distribute slips on the subduction plate, like so, these dots can be explained like that. There are many dots because there are on-land stations here, but these are the key observations that were only available from seafloor data. So with these incorporated into the inversion of the crustal deformation data observed offshore and on land, Inuma and others could say that the largest displacements took really near the trench. And if you use this deformation to generate tsunami, they are quite well explained. So that's the utility of offshore observations. And of course, they were only recovered after the earthquake, so it would have been really nice to have them real time. Now, Integrated Ocean Drilling Program thought we should do something, and they could quickly schedule a Chikyu drilling cruise, and they conducted what they called JFAST expedition, and the idea was to penetrate the plate boundary fold at the shallowest part of the subducting plate and place thermistor string across the fault plane. The fault plane was known from drilling, and people could put this thermistor string across the fault zone, and after recovered by an ROV. This is time, and obviously this is after the earthquake, and the data show that still it retained the heat generated by the friction, or you could also argue that that's the assumption we're making. But if we make that assumption, this is the heat, and to explain this heat generation, deduced from the thermal conductivity you found, and also the thickness of the slip zone, you can say that apparent friction coefficient was less than 0.1. This came up in a science paper in 2013. So this is the first evidence of penetrating through magnitude 9 earthquake and deducing the friction coefficient to be very low at this part. Of course, when it goes to 30 kilometers zip, one would expect that would be higher. So the Japanese government sort of agreed that we should prepare for these events with real-time observations. And so NIED, that's one of the government agencies, National Research Institute for Earth Science and Disaster Prevention, is now constructing this network of seismometers and pressure gauges. The total is like 6,000 kilometers cable with 150 stations. And the spacing is 30 to 50 kilometers depending on which way. And you can see that there is even a cable over on the other side of the trench. So this is basically planned and being deployed and to be completed this fiscal year, which means by the end of March next year. The data should be available to all researchers around the world, although the main aim is to monitoring the seismic activity offshore. This kind of data, I have no doubt, will really contribute in not just monitoring, but trying to understand what's going on offshore, where we really lack data. And another effort is going offshore central Japan by JAMSTEC. And its a configuration is different, but the idea is similar, except that JAMSTEC is focusing more on high-resolution data, and this is the Nankai Trough, where magnitude 8 earthquakes are believed to occur at 90 years to 120 years time, recurrence time, and most of the plate motion is, you can say that, taken up by these magnitude 8 earthquakes, whereas in Tohoku, until this magnitude 9 earthquake at this part slipped like 60 meters, we had thought that the seismic efficiency, which is how much of the plate motion is taken up by natural earthquakes, was estimated to be like 1/4 to 1/3. So we were wondering what's happening to the rest. And now we know part of the answer, that this once in a 1,000 years earthquake does the 100% release of the accumulated motion. But of course we want to understand what would be a unifying understanding of the difference that explains the difference between the behavior of Nankai and Tohoku, as well as other parts of the subduction zones in the world. We have still a long way to go. So I think I can basically skip this because I already spoke. And so in summary, again, oceans are technologically quite challenging and high risk, but you must know that the scenes of actions are out at sea. And I just found this cartoon, and this guy is looking for his quarter that he dropped under the lamppost, and the police officer asked, "Where did you drop it?" "I dropped it 2 blocks down the street." "Why are you looking for your money here?" "Because the light is better here." I guess you get the idea. I think you have to go where the action is. You have to go to places where there's hope for finding the answer. And this is a repeat of what I just said, what I said in the beginning. And finally, I would like to express my deep appreciation to all who work at sea and who support them. And thanks to my collaborating researchers around. Thank you very much.
Questions? No questions? So?
You've got continental crust forming in the island in the Arctic. How do you form it? I mean, you've got water coming up from the side, you've got a lot of things coming. How do you form that?
Well, it's not my thinking. It was really outside my expertise. But I guess audience, particularly from geophysical lab, may answer that. But how do you create continental crust? It's the same question, I think. And you have to melt the crustal material twice. You cannot make directly continental crust out of the magma from the mantle. So there must be a mechanism to remelt the early crust, but I don't really know the answer how that can be done. And I also don't know how could only that upper crust could be accreted and not the lower crust.
I mean, that's an interesting question, because one of the petrologic wisdoms for this is that you fractionate in the middle crust and you make a silicic mid-crust, but then you have an ultramafic lower crust. But you're not seeing these very high velocities that you would expect for that in lower crust. So the wisdom is that it falls off, but how and why and whether you've seen it yet. Yeah. Other questions? There's one here.
Oh, I just had a question when that network of sensors is going to be complete. What's the anticipated completion date?
You mean the networks that I showed?
Yes.
By mid next year, I think the data should be available. Or you can talk to me.
Those sensors are using, those stations are using pressure for differential for water depth, but is there any
Well,
attempt
they're
to
using
use-
parascientific digital.
but is there any attempt to get absolute
Yeah,
GPS?
they're getting absolute.
So what's the reference? Are there surface measurements as well? Ocean surface measurements?
Well, I don't know the details, but DigiQual's products are both relative and absolute. They are, so I guess they're calibrating before and after. They're looking at the frequency
But they're
change.
still not equivalent to getting GPS measurements on the ocean floor.
No.
Is there work being done to
But,
try
but they give relatively much higher resolution.
Sure.
GPS acoustic, to make them real time would be a challenge, but the recent development of, I mean, Scripps group is trying to use the wave glider, and that might be a hope.
Kiyoshi, come back to to overall the earthquake. The change in depth on the ocean, that tells you, I guess, does that give you a good handle on how deep the slip went, and how does that compare with the others?
They have that observation at the really shallower end of the pool. So actually, I think land observations better constrain how deep the rupture went, like 50 kilometers. Yeah.
Ellen?
I have a real practical question about the use of that new network along the Japan Trench. Given that the sensors right there will realize something's going on and send the signals at basically the speed of light to someone in Japan who then has to perhaps look at it unless it's automatically triggering. What sort of time delay is there between when, say, the P waves arrive and the tsunami arrive? How much of the time window do you have
Right.
for people to take action?
Yes, early warning is actually the surest thing of warning, and 30 seconds or more.
And for the tsunami, how much?
Tsunami would be 20, 30 minutes in Tohoku, but in Nankai Trough it would be minutes. So that's a challenge.
So how deep within the subsurface do you put these seismometers in the boreholes that you get these quiet signals?
Well, as I said, you need to go beyond the soft sediment, which is about 500 meters, depending on where you are. And actually, in the Japan Trench site, we had to go deeper than 1,000 meters. Still not too hard yet.
Because then like the water circulation underneath
The
will
shallow part is full of water, yes, unconsolidated.
I had a question, but you mentioned that these large earthquakes release most of the strike slip associated with plate subduction. But so what does this episodic tremor and slip do? That just
They
is
are
it a
very
different part of the fault and loads, or
well. Right. The main brittle fracture zone is different from where those tremors occur, and they occur either near the deeper end or the shallow end. But where exactly they occur is not very clear because it gets deeper. It's hard to tell whether they're actually on the plane or above the plane. If you go shallow, then you don't have instruments out at sea. But some people claim that they do occur in the shallower subduction plate boundary, but there are indications that they occur along the branch folds of it. But the energy release is small.
right? Any other questions? If not, Dr. Suyehiro will be around for at least a couple more days. So
Well, a week.
a week, okay. So go and see him. He's in the research building in his office, and